Welcome to the Cyber City Circus Presents Datasheet Digest. My name is David and I am your host today. Today's episode will cover the datasheet for the analog devices DS1307 I2C real-time clock. This datasheet is freely available from the Analog Devices website if you would like to follow along. If you would like to support the show, you can leave us a written review on Spotify or Apple Podcasts. We appreciate it very much. Thank you. First, we will start with a history of the part, a summary of the part, and its datasheet. Then we will critique the datasheet with our proprietary 555-point analysis system. I found a few different iterations of the datasheet, and we are using the datasheet marked revision 3/15. The datasheet and my show notes are found at www.datasheetdigest.com. This datasheet is packed with all kinds of great stuff, so be sure to check it out. The lineage of this part can be traced to Dallas Semiconductor. Dallas Semiconductor was founded in 1984. I spent some time researching this part to try to figure out when it first got into a catalog, and the best I can figure is that it was released around 1995. In 2002, Dallas Semiconductor was acquired by Maxim Integrated for $2.5 billion, and then, in 2021, Maxim Integrated was acquired by Analog Devices for a total of $20.8 billion. There is not an Analog Devices branded version of this datasheet listed on the Analog Devices website. We are using the one produced by Maxim Integrated in 2015. The following is the general description of the part from the datasheet. The DS1307 serial real-time clock is a low-power, full binary-coded decimal clock/calendar plus 56 bytes of NVSRAM. Address and data are transferred serially through an I2C bidirectional bus. The clock/calendar provides seconds, minutes, hours, days, date, month, and year information. The end of the month date is automatically adjusted for months with fewer than 31 days, including corrections for leap year. The clock operates in either 24-hour or 12-hour format with AM/PM indicator. The DS1307 has a built-in power sense circuit that detects power failures and automatically switches to the backup supply. Timekeeping operation continues while the part operates from the backup supply. Prior to reading this datasheet, I've never seen the term NVSRAM before, so I looked it up. NVSRAM stands for non-volatile static random access memory. Basically, it's memory that uses a battery backup, similar to how save game data was used in old Game Boy games and Nintendo games. When the battery dies, you lose all your SRAM. Continuing on this first page with benefits and features, the first thing it lists is that it has leap year compensation valid up to the year 2100. So let's talk about that for a second. Now, how you and I know about leap years is every fourth year, we add an extra day on February. So February has 29 days. This year is 2023, so it's not a leap year, but next year, 2024, is a leap year. So February will have 29 days. Now, normally 2100 would fall into that every 4-year rotation, but there's a special rule with leap years that doesn't get brought up very often. If the year is divisible by 100 but not divisible by 400, then it's not a leap year. So even though it says that it's valid up to 2100, all that means is that the year 2100 will have an extra day. And so the year 2101 would lag a day, and every year past that will lag a day, and so on. Depending on your application, it's probably not an issue. It also has 56 bytes of battery-backed general-purpose RAM with unlimited writes. So if your DS1307 is integrated into your system properly, you have 56 bytes of unlimited writable data that you can use on this. It turns out that the RAM on the DS1307 is 64 bytes, but it only needs 8 of those bytes to maintain the time and calendar. It also has a programmable square wave output signal. If you skip ahead to page 9, you see that we can change it to a number of settings, including a 1 Hz square wave, a 4.096 kilohertz square wave, an 8.192 kilohertz square wave, and a 32.768 kilohertz square wave. you can also disable it altogether. And there's power savings in that feature, and we'll talk about that later. Another benefit and feature listed is it has very low power consumption in battery backup mode. It says it consumes less than 500 nanoamps. 500 nanoamps is half a microamp. It's also 0.0000005 amps. So it'll run a very long time in battery backup mode. On page 6, where it discussed the battery pen, if you use a lithium battery of 48 milliamp hours or greater, it will work for more than 10 years in the absence of power. I extended that out some, and I did some math. If we use two AA batteries in series, that will give us 3.1 volts at 2,850 milliamp hours. And according to that math, it will last around 600 years. Also on the front page, we have the typical operating circuit. On this, you can see where the controller is, and you have your I2C pull-up resistors. You may be familiar with these being 4.7 k ohm resistors that you take your clock and your data lines and you pull them up to VCC, and that's in the drawing also. It shows each of the 8 pins, including the crystal. Now, the crystal's got to be a 32.768 kilohertz crystal, and that's defined later. But then it also has a pull up on the square wave out pin. And that's important because the square wave out pin is open drain. And so if you don't have a pull up on it, it won't act correctly. Also on the front page, we have the pin out for the integrated circuit. This integrated circuit comes in two different packages. It comes in an SO8 package and a PDIP package. The pin out between the two is identical, but the footprints will be very different. And on the bottom of the front page, we have the ordering information. There are 6 part numbers listed. Part number 2, 4, and 6 end with an N. The N indicates that it's for an industrial temperature range device. It's for negative 40 Celsius to positive 85 Celsius, where the standard device operates from 0 Celsius to 70 Celsius. So if you have an industrial application for this, you want to make sure that you get the N part number. Also, it has different part numbers for tube and tape and reel. Now, the PDIP package only comes in tube, right? But the SO8 package can come in a tube or tape and reel. And so it lists both of those part numbers for both the standard and the industrial temperature range device. Going into the second page, we'll start with the absolute maximum ratings. Something I've noticed that I've never really talked about, but it has a voltage range of negative 0.5 volts to 7 volts. And so you're thinking, it can't run at negative 0.5 volts in reference to ground. It's not going to. Well, what that means is if you pull the pin greater than 0.5 volts below ground, you may damage the integrated circuit. There's buffers and semiconductors and such inside the integrated circuit that if you did that, you're going to break it. So that's where that negative 0.5 volts comes from. Let's move down to the recommended DC operating conditions. Here it says that the recommended supply voltage is between 4.5 volts to 5.5 volts, where it's typically 5 volts. And that's pretty basic. We expect that. But if you go ahead to page 6, which we'll go over later, it talks about how that's not necessarily the case. That's the recommended DC operating conditions, but it can wildly vary depending on the battery voltage. And we'll go over that later. It also talks about what constitutes a logic high and a logic low. On this device, anything above 2.2 volts is a high, and anything below 0.8 volts is a low. The battery voltage is minimum is 2 volts to 3.5 volts, where the typical is 3 volts. Now, that's because the typical battery you would use with this is the CR2032, which is 3 volts. But it can go down to 2 volts. And again, on page 6, there's a lot of math associated with that we need to go over, and that directly affects the supply voltage. The next section is the DC electrical characteristics. When VCC is between 4.5 volts and 5.5 volts, meaning that it's powered, it says that there's a battery leakage current of around 5 nanoamps, which is practically nothing. And then it also talks about the power fail voltage when VBAT is 3 volts, which basically says that if the battery is 3 volts, that failover will take place at around 3.75 volts. And if the battery is at 2 volts, failover will take place at around 2.5 volts, which kind of contradicts the supply voltage from earlier. But I get that that was the recommended supply voltage. Of course, it's not recommending that you run it at 2.8 volts. And then the section below that is the DC electrical characteristics when VCC is 0 volts and VBAT is 3 volts, basically when it's in battery backup mode. When it's in battery backup, if you have your square wave output turned off, but your oscillator on, meaning that it's keeping time, but it's not outputting a square wave, it only uses 300 nanoamps or 0.3 microamps. While if you leave the oscillator on, meaning that it's keeping time, but you turn your square wave output on at a 32 kilohertz feature, then it's 480 nanoamps or 0.48 microamps. So you can see that there's a tiny bit of difference with that square wave output. And you also got to consider that if your VCC is 0, do you really need the square wave output? It's probably not tied to anything anymore because the power died and it's on battery backup. So you don't necessarily need it at that point. And there may be a way to mitigate that in power off of your microcontroller. And then when it's just in data retention mode, meaning that the oscillator's off, it's not keeping track of time, but it's keeping track of that RAM. Then it's all the way down to 10 nanoamps or 0.01 microamps, which again is practically nothing and could run basically forever on a CR2032. On the third page is the AC electrical characteristics. Now, you may be thinking that this isn't an AC device, this runs on 5 volts DC. Well, there are AC characteristics because it has data. And the only alternating current on the device is the I2C. So it's basically the parameters for the I2C data. It goes over the period of the low and high for the clock. It goes over the data setup time, which is 250 nanoseconds. It also includes the maximum rise and fall time of the data and clock pins. And if you add it all together, one cycle of the I2C bus is 10 microseconds, which is 100 kilohertz, which if you go to page 10, you'll see that it's listed as 100 kilohertz. And below that, it lists capacitance. It doesn't list the crystal's load capacitors, which are integrated, but those are listed later. If you download the show notes, you'll see on page 3 where I made a little drawing to show you what the clock signal actually looks like for the I2C bus. And it annotates the rise time, fall time, high period, and low period that adds up to that 10 microsecond cycle. Moving ahead to page 4, we have an example of a generic I2C timing diagram. It shows you the start and stop control signals and repeated start control signals. We'll go over that more later. And then below that, it has a functional block diagram where it shows all the pins and it shows kind of how it works on the inside. And if you notice here, this is the only place in the data sheet where it's actually listed. But you can see where the load capacitors for the crystal on the X1 and X2 pins are integrated into the oscillator and divider circuit. And to the right of that block diagram, you can see where the general purpose RAM is. And above that, you can see where the open drain connection is for the square wave outputs. Page 5 is our typical operating characteristics, and you have 4 charts. The first one is your ICCS versus VCC. This is your standby current draw based on the supply voltage. And then the second chart is your current draw on your battery dependent on the voltage of your battery. And you can see that there's 2 slopes on this chart. One of them's for when the square wave output is at 32 kilohertz, and the one below it is when the square wave output is in the off condition. And you can see where there's some real power savings in putting your square wave output off, especially when you're on the backup battery. More on that particular topic is found on page 9, and we'll get there. On the bottom line is current draw based on temperature. Remember, this thing operates at a specific temperature range, depending on if you got the industrial one or the standard one. And then the next one is variations on the square wave output frequency based on supply voltage. So as the supply voltage is lower, you see that there is a variation in the square wave output frequency. But if you look on the left side, we're talking about less than 0.1 hertz. So I don't think that that's necessarily an issue. And it may be for your use case. I wouldn't use this on GPSs or anything, but zero point 0.1 hertz difference as the supply voltage drops may not be much of an issue. Turning over to page 6, we have our pin descriptions. If you are trying to follow along, I recommend using the show notes version of the datasheet because it's highly marked up on this page. The first two pins are your crystal oscillator pins. They connect to a 32.768 kilohertz quartz crystal. The internal oscillator circuitry is designed for operation with the crystal having a specified load capacitance of 12.5 picofarads. The next one is the input, and X2 is the output. On the bottom, it says referred to application note 58, crystal considerations with Dallas real-time clocks. I looked that up, and it goes in more depth about the crystal, and we'll go over that more when we get to page 7. The third pin's your battery pin. It's designed for a standard 3-volt lithium cell, but it also says other energy source. It basically just needs 2 volts to 3.5 volts. If you're not using a backup supply battery, then you have to ground VBAT. VBAT has to be pulled to ground. This is where it says that a lithium battery with 48 milliamp hours or greater will back up the DS1307 for more than 10 years in absence of power at 25 Celsius. Pin 4 is your ground. Pin 5 and 6 are your I2C pins, and we're going to go over these in detail starting at page 10. But this is where it lists that the data and clock pins are open drain and require an external pull-up resistor. The 7th pin is your square wave out, and that's all programmable, and we'll go over that more later. And then the 8th pin is your VCC or primary power supply. This is where it says that when it's on battery backup supply, that read and writes are inhibited. But it's important to know that if it is on battery backup because VCC dropped below 1.25 times VBAT, that the I2C circuitry is disabled, it's inhibited. You cannot read and write to it. So you have to power it up on primary power to access the I2C data. But as long as the battery is connected, the data is still there. And then below the pin description, there's a section titled Detailed Description. On the first page was General Description, so this is just a more elaborate version of that. I'm going to read it out. The 1307 is a low-power clock/calendar with 56 bytes of battery-backed SRAM. The clock/calendar provides seconds, minutes, hours, day, date, month, and year information. The date at the end of the month is automatically adjusted for months with fewer than 31 days, including corrections for leap year. The DS1307 operates as a device on the I2C bus. Access is obtained by implementing a start condition and providing a device identification code followed by a register address. Subsequent registers can be accessed sequentially until a stop condition is executed. When VCC falls below 1.25 times VBAT, the device terminates an access in progress and resets the device address counter. Inputs to the device will not be recognized at this time to prevent erroneous data from being written to the device from an out-of-tolerance system. When VCC falls below VBAT, the device switches into low current battery backup mode. Upon power up, the device switches from battery to VCC when VCC is greater than VBAT plus 0.2 volts and recognizes inputs when VCC is greater than 1.25 times VBAT. The block diagram in figure 1 shows the main elements of the serial RTC. One thing in the detailed description that I don't think I really noticed elsewhere in the datasheet is when it talks about switching from battery back to VCC. It says that it will switch from battery to VCC when VCC is equal to VBAT plus 0.2 volts, but it doesn't actually start doing read and write until VCC is VBAT times 1.25. So if your VCC is VBAT plus 0.2 volts, it'll still be in air quotes battery backup mode, but it won't be running on the battery. On page 7, it talks more specifically about the crystal and the clock and the oscillator. It gives a table of crystal specifications, and it says that the accuracy of the clock is wholly dependent upon the accuracy of the crystal and the accuracy of the match between the capacitive load and the oscillator circuit. The capacitive load is 12.5 picofarads. Your crystal has a built-in impedance, and the 12.5 picofarads is meant to offset that impedance at the resonant frequency of 32.768 kilohertz. And then it says to refer to application note 58, crystal considerations with Dallas real-time clocks. I did that, and that's great. It actually gives a detailed explanation of how crystals work with integrated circuits. Table 1, crystal specifications, only really gives us 3 major specifications: your nominal frequency, your ESR, and your load capacitance. Now, the nominal frequency is 32.768 kilohertz. The load capacitance is 12.5 picofarads, but the series resistance, or ESR, is 45 kiloohm. ESR is the equivalent series resistance when the reactive component of the crystal resonates at the operating frequency. The lower the ESR, the better. This is saying that the maximum ESR you can have is 45 kiloohms. But again, the lower the ESR, the better you are. And then in figure 2, we have the recommended layout for the crystal. And this is really interesting. It shows how there should be a ground fill between the ground pin and X1 and X2, and it gives a recommended layout path for that. And that's for better shielding of your crystal. It also shows that you should have a trace keep out underneath the IC where X1 and X2 are. Laying it out how it's recommended in figure 2 is the best way to do it to help prevent noise in your oscillator. And on the bottom of page 7, we have a section titled RTC and RAM address map. This explanation is continued on page 8, but here it tells you that the RAM addresses for the real-time clock registers are hex 0 to hex 7, and then the registers that you're able to use for general purpose RAM is hex 8 to hex 3F. Another thing it tells you in this section that it doesn't really discuss in any other part is that if you're reading and writing data and you get to the hex 3F and it goes past that, it will wrap around to hex 0 at the beginning of the clock space, and it can corrupt your clock data, which is very, very, very bad. So if you're going to use the RAM built into the DS1307, it's probably best to write into your firmware a feature that will forbid going above hex 3F to not corrupt your real-time clock data. Going to the 8th page, we have a section titled Clock and Calendar, and this goes back to the RAM map from page 7. A few things that are important to note is that when the device is initially powered up, it will have January 1st, 00, first day of the week at 0 o'clock and 0 seconds. The most significant bit, or the 7th bit in the first register, is called the CH bit. The CH stands for clock halt, and by default, it is set to a 1 on initial power on. When it's set to 1, the oscillator is disabled. This is what you use to disable the oscillator. When you clear it to a 0, the oscillator is enabled, and then it'll start working. So by default, the clock won't do anything until you change bit 7 in the first byte to a 0. Next, it discusses bit 6 in register hex 2. Bit 6 in register hex 2 is used to determine if we're going to be using 12-hour mode or 24-hour mode. When bit 6 in register hex 2 is high, then bit 5 is used to signify AM or PM. And then bit 4 is used for the tens place of the hour, so it just counts from 0 to 1. You only need 1 bit. But when you take bit 6 and register hex 2 and you make it low, you put it in 24-hour mode, and then that changes the purpose of bit 5, which was an AM PM, but now it's the second bit in the tens place of the time. So where before it can count from 0 to 1, now it can count from 0 to 1 to 2, allowing for 24-hour readout. Below that, we have table 2, timekeeper registers, and this is really, really nice. It lays down all 8 bits for each byte in all the time and calendar addresses, which are hex 0 to hex 7. It tells you what each bit is used for and what you can do to change it. So, for example, this is where it tells you if you change bit 6 in hex 2, you can switch between 12-hour mode and 24-hour mode. At the bottom of the table, you see where there's hex 8 through hex 3F. That's your 56 bytes of user RAM that you can do whatever you want with. I know 56 bytes of memory doesn't sound like a lot, but this is 56 bytes of unlimited writable memory with a battery backup. Let's say you're designing a product that doesn't need a lot of memory. 56 bytes might be more than enough, and this might eliminate you needing to write to EEPROM or do any kind of wear leveling in flash memory because you can just use this SRAM. The following is what each byte is used for in order. Hex 0 is seconds, hex 1 is minutes, hex 2 is hours, hex 3 is day of the week, hex 4 is date, hex 5 is month, hex 6 is year, and then hex 7 is some control signals, and hex 8 begins your 56 bytes of user RAM. Turning the datasheet to page 9, we find a section describing the control register, register hex 7. There are only 4 bits in this register that have any function. Bit 0 and 1 are used as rate select bits for the square wave oscillator output. Bit 4 is the square wave oscillator enable bit, and bit 7 is the output control. There are 4 options for the output frequency, so there are 2 rate select bits, bit 0 and bit 1. Setting these registers can set the output frequency of the oscillator to either 1 Hz, 4.096 kilohertz, 8.192 kilohertz, or 32.768 kilohertz. Bit 4 is the square wave enable bit and is used to disable and enable the output oscillator. Set this bit to 1 when you want to use the oscillator. Just remember from page 5 that the square wave output will cause your backup battery to drain faster. And finally, bit 7. This bit is only used when the square wave oscillator is disabled. When the oscillator is disabled and bit 7 is 1, then the output pin of the DS1307 will read a constant logic high, and that will kill battery. So if you want to have it have no output there, you need to have your bit 4 square wave enable bit and bit 7 both low. Page 9 is a half page, but at the end of the section, there is a truth table explaining the control register in more detail. Starting at page 10 and ending on page 13, the datasheet gives us a full crash course on the I2C protocol. Using only the information found within this 14-page datasheet, someone should be able to write a fully functional and operational I2C bit banging script. Okay, buckle up. You're going on a crash course in I2C data communication according to the DS1307 datasheet. A copy of the show notes can be found at www.datasheetdigest.com. If you want to follow along, I've heavily annotated the datasheet and it's available to you if you want to follow along. Some things to go over before starting. I2C uses 2 connections for communication. It has a data pin called SDA and it has a clock pin called SCL. The controller is the I2C device that generates the clock signal. I2C devices on the bus do not generate their own clock signal. An I2C device cannot initiate I2C communication without the controller. The controller has to initiate the I2C communication. On page 6, we read that I2C pins are open drain, meaning that they need a pull-up resistor. The devices manipulate the signal by pulling it low, but in a resting state, it's at a logic high because of the pull-up resistors. Going back even further to page 3, where we found the AC electrical characteristics, it described the clock signal and shows the complete cycle adding up to 10 microseconds. Page 10 starts by introducing the control signals. There are 4 main control signals that are manipulating the data line during the high clock pulse. Whatever happens outside of the high clock pulse doesn't matter. Only what the data line is doing during the high clock pulse. I2C has 4 control signals. The first one is a not busy signal, a start signal, a stop signal, and an acknowledge signal. The signal and data being transmitted is dictated by what position the data logic is in while the clock pin is high. Before communication starts, both the clock and the data line should be pulled high because the I2C lines have a pull-up resistor on them. To start communication, the controller will change the data pin from a high state to a low state while the clock signal is high. Again, within the period of time while the clock signal is high, which on page 3, it says that it's 4 microseconds, the data pin will change from a high state to a low state. which on page 3, we see that the fall time of the data line is 0.3 microseconds. So in that clock pulse, it will start at a high and then go to a low. That signifies to every I2C device on the bus that we're about to start communication. Following this signal, the controller will send a 7-bit address that matches an I2C device on the bus. The 8th bit in the byte is a read or write command. This bit is high for reading data, and it is pulled low to tell the device that the controller is going to send data to write to its registers. Following every byte, the I2C device will send an acknowledge bit. The acknowledge bit is when the receiving device pulls the data pin low on the clock pulse following each byte. This is how every I2C communication starts. Following this, the controller or device will send bytes to each other, and they will send an acknowledge signal to each other. When communication is over, the controller will send a stop signal. When the controller wants to send a stop signal, it will let the data pin go from a low to a high during the clock's high period. On page 3, we see that the rise time is 1 microsecond. That covers all the control signals. There's also something called a repeated start, but that's used to move the pointer and then read from a pointer, and we'll go over that later, I promise. Everything else on the I2C bus is with addresses and the read-write bit, or it's data that is being delineated by the acknowledge bits. Continuing down page 10, the datasheet tells us that the I2C bus can operate at a standard mode of 100 kilohertz or a fast mode of 400 kilohertz. But the DS1307 only operates in 100 kilohertz standard mode, which the standard cycle length is 10 microseconds, which we confirmed on page 3. Flipping to page 10, we're presented with figure 3. It shows a good example of what the data and clock lines look like. On the show notes, I've annotated this drawing for this episode, and it's a really good drawing that may help if you're having trouble. Before we start page 12, let's do a quick review. Clock pulses are generated by the controller, not the device. Start and stop signals are generated by the controller. The acknowledge bit is always sent from the receiver and sent after every byte of information. Data is always sent with the most significant bit first. When reading a device, the device will read from where the register pointer is or from the beginning. Pages 12 and 13 show the 3 communication protocols within the I2C standard. There's data write, where the controller writes data to the device. There's data read, where the device reads data to the controller, starting from where the register pointer is. And then there's write pointer data read, where the controller points an address and then reads from that address. Let's go over them. Data write goes like this. The controller sends the start signal, a 7-bit address, followed by a 0, which tells every device on the I2C bus what address you want to communicate with and that you want to write to it. The device sends an acknowledge bit, which pulls the data line low on the following clock pulse. This is followed by the controller sending a register address that it wants to write to. This is again followed by an acknowledge bit from the device. The controller sends bytes of data. The device sends acknowledge bits for each byte, and it keeps writing until the bytes are finished. When it's finished, the controller sends a stop signal. Both lines return to a not busy condition with both lines pulled high. Something to remember from page 7, if you're writing data to the flash, when you write past address hex 3F, it will wrap around to register hex 0, and it will overwrite your clock data. Data read goes like this. The controller sends the start signal, followed by the device's 7-bit address and 1 bit. The device sends an acknowledge bit. Then the device sends the first byte of data. The controller then sends an acknowledge bit following each byte that the device reads out to it. When the controller is finished reading, the controller will send a high bit instead of a low bit on the following clock pulse and then send a stop signal. Something about data read to remember is that when you start reading, it will start reading wherever the register pointer is when you sent the command. Also, the device will continue to send you data until you tell it to stop by sending a stop signal. To tell the device what register you want to start reading from, you need to do what's called a write pointer data read. To do this, we tell the device we want to write to it. and then we tell it what address we want to start writing to. But then in the last minute, we send another start signal followed by an address and the read bit, and then we just start reading. So it moves the register pointer, and then we just start reading. It goes like this. The controller sends a start signal followed by a 7-bit address and a low write bit. The device sends an acknowledge signal. The controller sends the register address that it wants to write to. The device sends an acknowledge signal, and the register pointer has moved. Now the controller sends another start signal followed by the same 7-bit address from before, but now it has a high read bit. The device sends an acknowledge bit and then starts out the first byte. The controller then sends acknowledge signals until it's finished reading. When the controller is finished reading, it will send a high not acknowledged bit followed by a stop signal. You will almost always read data in your firmware in this way because it moves the register pointer where you want it to be when you start. Then at the end of page 13, we have some package information. In the PDF, it has hyperlinks to the dimensional drawings for the part, but these links don't work. They all redirect to a 404 page or to Analog Devices homepage. I have a link to these drawings in the show notes. Since the links in the document do not work, these drawings do not include any suggested footprint layout for the PCB. Turning to page 14, the final page, we are greeted with a revision history. At first, I was surprised. This is the first data sheet on the show that had a revision history. I thought it would be fun to look up older iterations of this data sheet and found a bunch of iterations from Dallas Semiconductor and Maxim. It would seem that the revision history is missing a few iterations. I was able to find 5 different iterations of the data sheet. They are, from order of oldest to newest, revision 081800, revision 100101, revision 071405, revision 100208, and then this one, revision 3/15. These are all available from the show notes on www.datasheetdigest.com. One thing I wasn't able to find was an original datasheet from 1995. Again, I'm not exactly sure when this device was released in a catalog. The oldest datasheet I was able to find was from 2000. I don't know if Dallas Semiconductor was digitizing datasheets before 2000. Maybe that's why I can't find it online. If someone has a late 90s Dallas Semiconductor data book and they wanted to donate it to the show, my address is on the website. That completes the review of the DS1307 datasheet. Now let's start our proprietary 555-point datasheet evaluation and analysis report. This report is found in the show notes at www.datasheetdigest.com. For presentation and accessibility, I gave this datasheet 61 out of 75 points. There are some foreign language translations available, but they all seem to be done by academics working for colleges. There are hyperlinks on the PDF, but none of the hyperlinks actually work. Moving forward, this datasheet got 50 out of 60 points for organization and layout. There's no table of contents and navigation, so it lost those points. Electrical characteristics, section 3, it received 76 out of 90 points. Nothing really noteworthy there. For section 4, functional description, it got 75 out of 75 points. I don't know how it could have done it better. It laid out the entire I2C protocol in the datasheet. That's a pretty good functional description. Section 5, application information, it received 34 out of 60 points. Again, there's no PCB footprint and layout in the datasheet. There's hyperlinks, and all the hyperlinks are dead, but the documents they were linked to don't have the layout anyways, so it doesn't matter. So I got 0 points there. Component selection and guidelines are listed in the datasheet under App Note 58, but there's no hyperlink to App Note 58. I looked up App Note 58, and there's a link to it in the show notes, and it's pretty good. It's a worthwhile read. 34 out of 60 points. Quality and reliability, 7 out of 75 points. There's really no quality or reliability information in the datasheet. It does say that it's UL recognized, but that's about it. There's some battery data for reliability, so I gave it 2 points there, 7 out of 75 points. Section number 7, packaging and handling, I gave it 0 out of 30 points. There's no packaging information. There's no handling information. Section 8, support and documentation, I gave it 13 out of 60 points. There's design resources with drawing and schematics, but that's about it. Additional documentation, it calls for documents, but the links are broken. And community resources, I couldn't find any resources from the OEM brands, but there's tons of resources online, Adafruit, DigiKey text forums, no shortage of ways to use the DS1307. Section number 9, updates and revision control. I gave it 10 out of 30 because the revision history is incomplete. And then section 10, overall impression, I gave it 15 out of 15. So the total points awarded to this data sheet is 341 points. This is a great data sheet. It probably could have been 2 pages shorter if they had better white space management, but it's fine. Analog Devices hasn't updated it at all since they acquired Maxim Integrated, which is okay. I wish that the hyperlinks on it worked, but whatever. Overall, this is a really good data sheet. It's very captivating, especially when you get to page 10. Definitely recommend this data sheet. Well, that brings us to an end of this episode of Datasheet Digest. A little bit of trivia today about the DS1307. Did you know that the DS in DS1307 stands for Digital Sundial? It's a fact. You don't have to look it up. Just take my word for it. Be sure to follow us on Twitter with @Datasheet Digest. If you would like to support the show, please leave a written review on Spotify or Apple Music. We're also available on Audible. I can't wait for the next episode, and I'll see you next time.